Okay, so this is chapter 3, where we're going to be talking about the relational model. A couple things we're going to be talking about. The relational database, what it does is provides a logical view of the data. And we're also going to talk about the basic components. But there's a couple different types of databases that are out there. The relational database has a particular construct uses what it calls relations. Um, these relations, which we also can call tables, are made up of rows and columns, or as we call them here, tuples or attributes. And these tables, or these relations as they were, are implemented as tables in a relational database management system. All right, we're also going to talk about some of the things around related to relational database operators, the data dictionary, the systems catalog, which is some of the internals. Talk about how data redundancy is handled, and also some of the concepts around indexing. All right. So to start off, this idea of we've used this term a couple times over the course, and you're going to hear it again and again because basically that's what a database is. A database does provide a logical view of the data, which it's a representation of the data and the different relationships. All right. So the objective of this stuff is to create something that's logically simple. So you have simple and effective database design, basically implemented through simple and effective database design methodologies. And also the idea of facilitated, logical view is facilitated by the creation of data relationships based on this logical construct, which we call a relation, aka a table. Right. So here's some of the characteristics of a table, relational table. It's a two-dimensional structure, rows and columns. Uh, each row represents a single entity within what we call as an entity set. Each table column represents a entity set being a collection of all of the different rows. Table column is an attribute, and each column has a distinct name. So everything has to have there's a uniqueness. You'll see a couple places inside of relational database theory where you have to have uniqueness as an attribute in order to make this stuff work. The intersection of each row and column is a single data value. All right, and every value in the column is the same data format. So if you say something in a column is a date, everything in that same column is also a date. Has a range of values known as the attribute domain. Actually, the order, one of the things that's interesting about it, the order of rows and columns is really immaterial. So what happens is when you're loading stuff in, it just sticks it at the back end. Right? It can find it. And there's functions it will look at where you can sort it. All right, so you don't have to sort things up front, and you don't have to go through a lot of overhead of trying to figure out where something goes and moving stuff around. Basically, data get inserted at the next logical point, and it's accessible across the entire data set. And finally, this last point here, each table has to have an attribute or combination of attributes that uniquely identify each row. So we'll talk about we'll talk about some of these different characteristics as we're moving forward with this. Let's talk a little bit about this idea of this unique attribute. Well, there's the concept we call inside of relational databases is something called a key, right? And what it is one or more fields that can determine other attributes. So the idea is you can use a key to make sure that every row is uniquely identifiable, right? And you can also use it to establish the relationships across tables. We used our analogy of apples and snowplows. There's nothing in common. In order for relational databases to work in terms of being able to access information spanning multiple tables, you have to have something that links them together. All right. And you also have to make sure that the data is the integrity of the data is maintained. We'll talk about that in a little bit as well. The primary key, so the identifier that we use that this makes each row unique is something we call a primary key. And it's a field or attribute or combination of fields that uniquely identifies any given row. All right. So the so if you have one field that is unique in a row, then that row is considered unique, and that field is considered the primary key. It can be a single field. It can be a bunch of fields. It can be um, actually a lot of times what happens is you put a fake key or what they call a surrogate key, which is basically a sequential number. So what you do is you say, okay, what's the key of this thing? We have a field. The key field is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 because that's the only row in that table that's going to have that particular value. But it's an attribute that is enforced inside the relational model. Every row in a table has to be unique. So the determination, a couple concepts. Basically, it's a state of knowing value of one attribute makes it possible to know values of the other. Right? So this kind of goes back to your core relational theory. It's kind of goes back to also the basis for establishing the role of a key and the relationships between attributes. So, for example, you'll take an address. An address is made up of the street. It's made up of the city. It's made up of the state. It's made up of the zip. All right. So it's something we can use inside of in the data structure to be able to describe the relationships between all the different attributes. Also, there's a concept called dependencies, which is related to that. Basically, value of one attributes will also determine the values of others. All right. So there's what they call that's what we refer to as a functional dependence. All right. And those are broken down into two things. You either have the determinant, which is what determines the value, and the dependent, which is what the subordinate is, or what you are associating with. All right. So what we have within this is, basically another means by which we can define data and can work with it. Usually don't see in real life, a lot of real life, the concepts of determination and dependencies, you usually don't see a lot of it. I mean, it's there. It's there as part of the formal definition of the stuff. A little bit more information about keys, as we talked about keys. Composite key. A key is composed of more than one attribute or field. All right, so a key can be as long as you want, so long as it has at the outcome, the combination of all those fields makes that particular row unique. All right, so you can have one field. Obviously, if you have a sequential number, that would be the field. But you can string a whole bunch of fields together, as many as you would need. Ideally, you'd like to keep it in one, maybe two. If you have a composite key, basically every one of those attributes or the fields considered part of the key. Right? Entity integrity. This is actually, there's a couple core what we call integrity definitions. This is a key part of relational theory. A condition which in each row has its own unique identity. Basically, everything's got a master key. Every field is a key, or every row has a key, and every key in the row makes that row unique. A couple other concepts here. We talk around null. Null basically means it's a absence of any value in a field. It's not the same thing as a blank. A blank is a blank. All right, blank is a field. A null is nothing. Basically, so if you see something being defined as null in a database, it means there is nothing in it. So, it's not simply that it's a blank, but there's nothing in it. The other concept, we talked about this entity integrity. This other concept we talk about within databases that kind of make relational databases work is what we call referential integrity. And what that means is, talks about the relationship between two tables. All right, and in this case, every reference to an entity instance by another entity instance is valid. That's a very formal definition. What does it mean exactly? Well, basically, what happens is you have two fields in common. You have two tables that have a field in common. All right, and that's what you use to link the two tables. All right, the field in one equals the field in the other. What happens with referential integrity is that every field, every value that is assigned to fields in one table are also represented in the other table. All right. So if you have, say, for example, table A, and you have, 1, 2, 3, 4, 5 in that table, in the other table, the set of values you can only have are 1, 2, 3, 4, 5. If you have the number 6 or 7, 8, 9, 10, any other number, but what's in that set, what will happen is that actually what that's referred to is it breaks referential integrity, which if you're a database person, that's a bad thing. So basically means the database is not valid. The results you get will not be valid when you execute a query. All right. So this whole idea of referential integrity, where all the values in one table are also represented in the other table, that is something that is something that is enforced in databases as a rule, and is actually in real life. There's actually utilities and programs and stuff can be doing to verify and check on that. Because when you break a database, basically what that means is what you get back cannot be trusted. And then secondary key, the key used for data retrieval purposes. So this is kind of a picture of a simple relational database. Right? Two tables, right? Two relations, as we were. First table is product table. The primary key is the product code. All right. And it has a prod code, prod description, prod price, on-hand quantity, and then the vendor code. All right. And the vendor code would be where you would buy that from. So if you're, say, for example, you're a store and you're buying from different suppliers, what you would have would be, the different suppliers would be the vendor code would be represented in the vendor code. All right. Now the vendor code is the other vendor table. All right. So the primary key on that is the vendor code. All right. And the idea is what will happen is if you want, you can link these two tables together. All right. There's a common field. The common field in this case is vendor code, vend code. You can actually link things together. The field names don't have to be the same, but it certainly makes things a heck of a lot easier if you make the field names exactly the same when you have between two tables, linking two tables together. All right. Now, what will happen is what this represents is for every as we look at the relationship between the product and the vendor. All right, so every product should only have one vendor. All right, but one vendor can supply many products. All right, if that makes sense. So, say for example, here in this table here, we have vendor 232, vendor 232. We look here, that's going to be this Annalise Cristal is the vendor contact on that, the vendor code, and that's their phone number. All right, so if you did a lookup and say, give me a list of everything, give me the phone numbers of everybody who is all the products and the vendor code, the vendor contact information for everybody with vendor code 232, what you would get is basically a list of these products as well as the contact and the phone number for Annalise Cristal. We'll be looking at this more in depth. It's just going to give you a first view of a simple relational database. All right, so more definitions around keys, and so once again, this actually goes into kind of more in depth around relational theory. You think concepts of super key, candidate key, primary key, foreign key, and secondary keys. The ones that are the most important, the ones we're going to be talking about the most here is what we call the primary key and the foreign key. Right? Primary key is what is used to uniquely identify a row. So as we say here, uniquely identify all other attribute values for any row. Cannot contain a null entry. And then the foreign key, which is an attribute in one table whose values must match the key in another table. All right. So what we're looking at as we look at this here, this is the foreign key right here. As I said, the vendor code is the foreign key, which matches the vendor code in the vendor table. A bit more about the integrity rules. As I said, this is very important because basically the way databases are designed, relational databases are designed, is if you do it the right way, the answers you get are correct. If you don't set it up the right way, the answers you get may not be correct. All right, so that's kind of an important thing to keep in mind. The correctness of your result set is a function of how well the database is designed. So we talked about what a entity integrity is. Basically, it means every row has a unique key. And then referential integrity, it means that that between two tables that are related together, there is a common set of values from one to the other. So the idea is if one table has values that are not represented in the other table, not represented in the foreign table, and you can get to a situation like that where if you were to delete, and we'll talk about deleting and things like that, but the implications are sometimes when you delete something, you'll have something left. You'll have rows that are left behind, like orphans. All right, you take something out of the one table, and then everything in the other table that has the same foreign key or has the same key that was associated with that are orphans, which basically means you can never access them when you're asking, when you're doing a query. So this is a key part of around that all tables in a relational database have to maintain and sustain referential integrity. So just some examples, and we've talked about this, the examples of the integrity rules. Every row in this has a unique key. Primary key is cuss code. If you go through this, every cuss code is unique. Each one is different. The foreign key in here, all right, agent code here is either matches 501, 502, 503. So you either matches everything, or you have a null. That's a kind of an exception. But basically, what you do is all the values that are here are represented here. All right. If you had a 525, you'd have a broken. If you have a 525 here and there's not a 525 here, you have a broken database. So we talked about the basis of this stuff. So now, why do relational databases work? Well, they work because they're based on mathematics. So this is relational algebra. So relational algebra is a theoretical way of manipulating the table contents using these what they call relational operators. So we'll talk around some of this stuff here, this rel, var, relation, and closure are all related to relational algebra. So one of the things that's interesting about relational algebra, we use commands, we'll use SQL commands, we'll use to do stuff with the database, but we're not really thinking in terms of relational algebra per se. It isn't necessarily relational algebra. It's based upon relational algebra. All right. So within relational algebra, relational algebra describes what it's designed to do is describe the operations of sets. All right. So the idea is you have two sets of things, which we can represent them as tables. Say they can be represented as tables. All right. So the idea is that you have a set of operations you can perform on that table. So you can basically go through a table and identify and create a subset of the table, Or you can combine two tables together, all right, a union where you can combine the results of one table to the other table to another table, and all the unique values. Or that's a union. Or we can have an intersection, basically everything that where two fields match between two different tables. So the ones we use, the things we use in relational in our relational work is the select is a command, and then intersect is also conceptually we use this, but everything the command we'll see is in this whole SQL language that we're going to be working with is this idea of a select command. So the idea is original tables. If you do a select on all fields, basically you get a copy of the field. All right. If you select only the price less than $2, right, you create a new table. Basically, you create a new set, all right, which contains everything that has a price less than $2. All right. And if you select only code equals, whatever the P code is here, obviously there's only one if you go against the unique value. All right. So what happens is, if you think about what select is doing, basically what select commands are doing, they're making big things and turning them into small things. Right? You're reducing the set. You're creating subsets of an overall master set. So everything that's in a table can be considered like the master set of data, and the results of everything a command select runs against that creates a subset of values based upon some criteria. Right. Some examples of union and intersections, kind of the union would be, the combined results of both of these tables together, with taking out dupes. Intersection is, basically matching, what is the one field, which records we have in common. So in this case, we have only one record in common between these two. It's Franklin Johnson. All right, so if we intersect these two together, our result set, as it were, is Franklin Johnson. All right. There's only one things that match. If there was a Martin Lopez over here, you'd have two. All right, or so on and so forth. So just as kind of a quick recap of this, difference yields all rows in one table not found in the other. What's in one table and what's not in the other. And then, product yields all possible pairs of rows between two tables, or the fancy name for that is a Cartesian product. Basically, you take all combinations of everything between two tables and you create that's your result set. An example is from a difference. All right. So everything that's in one table but not in the other. All right. So George Jones, Jane Smith, Peter Robinson, and Martin Lopez are in one table but not in the other. All right. Franklin Johnson is a field that is the name that's in that's a common. All right. That's what we call difference. And then product is as we said, the combination of everything. So we've got, 3 rows here, or 3 columns here, 3 columns here. And we have 1, 2, 3, 4, 5, 6 columns here. And the combination of both of these together. So from a relational database perspective, what we do is we use we have here where we're talking still kind of theoretical relational set operators, but we use this idea of what we call a join. So basically, what you're doing is when you're taking two tables and you're combining them together, it's what we call a join. The data can be combined from two tables to create a whole new set based upon whatever criteria you would like. And you can do it with 2 tables. You can do it more than 2 tables. It's not just simply 2. Actually, some of these things can become can appear to be very complicated. But once again, if the database is defined correctly, the results we get will be correct. Divide, this is kind of more of a theoretical. We don't really use a lot. You don't see a lot of this. We see a lot of joins We don't necessarily see a lot of defines, but it's in the it's in the theoretical basis. Types of joins. A natural join, basically a natural join is basically all rows with the common values and the common attributes. All right. So basically, you select two fields, and you look for the common attributes between two fields, or the common values of attributes between two fields. An equijoin is links the tables on the basis of the conditions to compare specified columns of each table. All right, so you can do multiple fields. So you get this and this and this and this. All right. And theta join is what we call extension of natural join, denoted by a theta subscript after the join symbol. It's but basically what it is how you can link two tables together. Inner joins, outer joins, left outer join, left inner join. Inner join means only the match records from tables are being only the match records from the tables that are being joined. That's the only thing that's going to come back. In outer joins, match pairs are returned and unmatched values are left null. So everything is in one table but not in the other. And you can do it either way. Everything is in one table but not in the other. Everything in or the inverse of that. All right, between the first and the second table. All right, so inner joins are, and both of these all these things will come in play. So these types of joins, inner joins, outer joins, are all things that we actually will see in real life, in real life scenarios, real life situations. Right. So this is kind of an example here, from a divide. Data dictionary, system catalog. These are some of the inner workings or inner components that are inside the database management systems that basically let the database do its magic. All right, so data dictionary, description of all the tables in the database created by the user and the designer. System, which is different than the system catalog, which describes all of what we call the objects in the databases. All right, so as we say here, homonyms and synonyms must be avoided to lessen confusion. So what you want to do is you want to use, you want to be consistent and unique in your naming, because otherwise if you, start calling the same thing, the same item, different things, or different items, the same thing, in your database, very quickly you won't know which way is up. So we talked about this idea of relationships. This is one of these fundamental backbone concepts in this. So we have the relationships between databases. You have a one-to-many relationship between tables. It's probably what we see a lot of in relational databases. We see one-to-one. Also one entity can only be related to one other entity and vice versa. Right. And then you can have a many-to-many. Right. And then you can also see what they have here, composite entity, bridge, and associative entities. Usually not that, you don't see a lot of that, but you do see these. So this one-to-many is really the kind of the backbone. We will see lots and lots of this. One-to-one, many-to-many, there will be scenarios where we'll actually be seeing that as well. So your relationship between, in a lot of ways, the best way to describe a lot of this stuff is going through examples. So the example we're going to show here, relationship between a professor and a department. Professor is part of one department. That's a one-to-one relationship. Or we say chairs, but it could also be is member of. A one-to-n relationship, and actually what you can do is you can do an end-to-end to two one-to-many relationships. So you can do is you can say, so you can combine things together. You can kind of create these things as a single relationship and then combine them together. So you say if a student has a class, or the student enrolls in a class and shows in the class enrollment. So there's a couple different ways to look at this, depending upon the circumstances, but depending upon what you're trying to model. you have a lot of flexibility to kind of show different things in different ways. Expanded AR, basically this student registers in class associated the course. All right. And once again, all these relationships are two ways. All right. So this is going to be a one to many. All right. So a course can have many classes, but a class can only have one course, because that's the foundation. All right. So that's kind of, so you always want to remember that. You can see this on both. You see this on both sides. Talk a bit about data redundancy. The idea of all these keys, this idea of uniqueness, all of these things. Really, what you want to do is it helps control data redundancies in a database. All right. Now, ideally, what you like to do is you'd like to say, okay, you're going to have one reference to any, there should be only one thing that's referenced in a database. The reality is, that is a good rule, but it is also not necessarily hard and fast, because there are circumstances in which you may have more than one more than one attribute representing the same things. A lot of times you'll see things like, for example, in terms of for performance reasons, you'll kind of duplicate something between of one attribute to maybe another table, primarily just more for not necessarily because what you're looking to do is find a way to make things faster, make it more critical information, as you say here, crucial information purposes. All right, but generally, the general rule is, you want to eliminate redundancy except when except when you need to use it for whatever specific purposes. So this is where we talk about invoicing. So this is an example of an invoice. All right, with a bill. All right, so a bill is, a customer has a bill. All right, for stuff they purchased, and there is on that invoice there are multiple lines, different things that were purchased, which then translate also back to a definition of a product. All right, so we represent these different one-to-many relationships. One customer could have many invoices. One invoice could only have one customer. An invoice can have many lines, but each line can only be associated with one invoice. All right. So it's kind of you have to kind of think of this stuff as kind of the views of this being is kind of seeing this in two ways. So indexes are a means by which you can actually speed things up. So it's kind of it's something that's been added to a database, to relational databases, to streamline things. Because what will happen is if you're doing a search on something and there's a million rows in the table, by default, what you'll do is you'll look at a million things, all right, to figure out if something is in there or not. And that can take up a lot of time. So the idea is indexes were created to kind of give you like a shortcut capability to kind of give you provide a means by which you don't have to look at every row. You can look at things in a kind of a shortcut fashion. All right. So the definition here: orderly arrangement to logically access rows in a table. So you have in each table, each index is associated with one table. All right. And a table can have many, and a table can have many indexes. So just to wrap up here, all right, so this is Dr. Codd, when he put this together, he created 12 relational database rules. All right, so this is the foundation, once again, kind of he's the gentleman who did the translation of relational algebra into a database form, right, to be able to use it in a database. So he created these 12 rules. All right, so you'll see things like guaranteed access, systematic treatment of nulls, comprehensive data sublanguage, view updating, high-level inserts, physical data independence, logical dependence, distribution independence. Basically, what these 12 relational database rules are, they're kind of the high level. They're really high-level guidelines And what happens is in real life, most databases will respect most of these rules. All right, though you don't have to follow exactly Dr. Codd's all 12 rules to create a relational database. You can create working relational databases that are less than perfect. All right, but uh, however, you need to follow enough of the rules and enough of the guidelines to be able to make it a usable database. All right, so there's sort of kind of a line, and we'll be kind of talking, we'll be looking at that as we go through. So it's like as a former boss of mine used to say, perfect is the enemy of good. So the idea is a lot of times with databases, you want to make it good enough um, to work, less than ideally perfect in Dr. Codd's eyes. All right. So that wraps us up for this particular topic.